Okay, so hi everyone, good evening and welcome to the May evening lecture organised by the IET Central London network. I'm Rimesh Patel, a volunteer for the IET Central London network, and I'll be your host for today. We also have Matt Davies, who's also going to be co-hosting the session. We're a group of volunteers who organise monthly engineering events that support the IET's mission, which is to inform, inspire, and influence, just like today's lecture, which is on the topic of face masks. Our speaker for today is Dr Myant, Senior Lecturer at Imperial College London. Before we get to the lecture, we have a few housekeeping announcements to make. So firstly, as the data privacy notice, we're letting you know this webinar is being recorded, where audio and video features are disabled for all delegates. Secondly, we have enabled the Q&A box and its ability to perform upvoting, so please take advantage of that or indeed ask your own questions. Thirdly, the chat box is also enabled, into which we're going to place the link for you to obtain the CPD certificate. And towards the end of the lecture, we're also going to put in a short diversity questionnaire from the IET, so please do take a moment to complete that. And finally, as said, the entire webinar is going to be recorded and it's going to be made available via our YouTube channel and our blog. So with housekeeping over, I'm now going to hand over to Dr Myant. Thank you.
Great, yeah, thanks everybody for joining us this evening. So I am going to talk about face masks and what we've been doing in this area over the last year, and kind of walk you through the journey of why we got involved in this area of research, what we've learned, and what I think the future holds for this sort of particular group of products or industry as a whole. I want to just spend the first few minutes, first 5-10 minutes, just giving a little bit of background about myself, about the kind of research that I do, and hopefully just sort of provide some foundation to why we got involved in looking at face masks. So my name is Dr Myant. I'm a senior lecturer at Imperial College London. I work in something called the Advanced Manufacturing Group, and I also teach design for additive manufacture at Imperial College. That's a module that's open to all engineering students across the Faculty of Engineering at Imperial College. My main research areas is additive 3D printing, the development of the technology as well, in particular bio printing, and an area of engineering called tribology as well. For those of you unfamiliar with Imperial College, this is where we're situated, which is in a absolutely lovely area in London, up by Hyde Park, very near the Royal Albert Hall. And my department, which is the Dyson School of Design Engineering, is located right here. We are right next door to the Science Museum. We're also the newest department within the Faculty of Engineering. We've been running for about 5 years now. For people a little unfamiliar as well with what we do at Imperial College, we only really study and teach engineering, sciences and medicine. We don't really do anything outside of that, and we like to consider ourselves one of the top universities in the world for that area of research and education. So as I said, I'm one of the group leads in the Advanced Manufacturing Group. We're a medium-sized group at Imperial with about 6 postdocs, research assistants, and about a team of about 13 PhD students. So we do everything around 3D printing. We also look at concept of lightweighting and optimization, and we also look at biomanufacture and microfluidics. And the kind of projects that we do within my group can sort of stretch from, say, the technology development and the application of 3D printing into sort of new product concepts, new materials, things like metamaterials, but all the way through what we try to establish through that work is also design tools, sophisticated or smart adaptive tools to enable other engineers and other designers to get the most out of that manufacturing technology. So we kind of like to say within the group that 3D printing can actually do a lot more than we ask it to do. And part of our mission statement is to discover and develop, establish those methodologies, those design approaches, the technologies, the tools to enable us to get everything from that manufacturing technology. And the kind of projects that we then do with that, the kind of, sort of real world applications that we try to do with that is this sort of constant theme of wearable technology, typically for medical uses. So in this instance, what we have is a kind of an advanced scale like structure. So we've developed a material that behaves and is sort of mimicking the behavior of scale structure found in nature, and then we apply that into sort of protective and therapeutic wearable products. We also have a project running where we take things like x-rays, and from the x-ray we can predict a 3D model of a bone, and from that we can design and develop customized joint implants for patients. And the whole process, or what we try to achieve by the end, is this whole process is completely automated to allow it to become scalable and viable, cost effective to healthcare services around the world. And this is the sort of constant theme that we're trying to do, is build this sort of customization into what we do. So there's the design process of the customization, of collecting the data and designing the product, but it's all enabled through 3D printing. And that's something that we're going to kind of talk a lot about with the mask as we go through. So where our mask journey began about 2 to 3 years ago now, I had a PhD student, Shia Lee, who's going to feature quite prominently through this talk, started her PhD looking at developing automated design processes for the customization of personal wearables. And her main focus at the time was something called a CPAP mask. And we looked at utilizing a method of taking a 2D image of someone's face that you can just capture on your mobile phone, and from that we can find key landmarks on your face, say your eyes, nose, mouth, so forth, and then we can use a statistical model to predict the 3D shape of your face based on the kind of 2D separation of those points. And then from that 3D model of your face, we can automatically build up a customized mask for you. And this really served as the sort of foundation for the rest of our work, which was kind of COVID related. And the sort of phrase that I've used, and I'm going to keep using as well throughout the talk, is this concept called mass customization. And I want to kind of give a definition to that so that hopefully it's clear for everybody. Mass customization is sort of a very simple concept where every product service that you are given or you pay for is completely tailored to you. So the idea is that the experience of buying any consumable is like going to the tailor. It's like having your clothes tailor fitted to you every time. And this is in contrast with what most of us experience in everyday life, which is the sort of design process called modularization. That is where we limit the number of choices you have. And so in clothes and in many other products, that's done in sizes, typically just small, medium, and large. There might be a little bit more variation in that. And the idea is that there's enough variety that you feel like you were able to customize that to you. So you could go to lots of different shops, so there's lots of different brands on offer, and they all have a slightly different cut, a slightly different sizing, and you were able to pick out what you wanted, so you felt that your outfit has been customized just to you. But in reality, you've actually had a very limited selection. And that's kind of like, these are the two key concepts that are really important to the rest of this presentation. And we'll keep sort of repeating this and revisiting this, because this is really where we start out from in the masks. So face masks, you know, why we term this the unexpected industry, and I think everybody will remember this day. So 23rd of March last year, I think it was a very it was probably the day that for most of us, COVID, the threat of COVID, the reality of it, really hit home. And that was the day that we all entered into the first lockdown. And that's kind of, it was during a period after this that everybody started to become very aware of face masks, and it became one of the most talked of topic on the news, amongst your friends, whatever. And particularly I think in the UK, where we didn't have a history or a culture of wearing face masks, it's became a really big point of trying to understand why we should wear them, what's the importance of them, and you know, what role does it play for you, for others, and you know, are they effective? So this really started out our journey of trying to consider whether or not our work on customizing things like CPAP masks and other products could be applied to face masks. So we really wanted to understand what the role of the face mask is, what makes a good face mask, what makes a face mask effective. And I think coupled at the same time, what we saw with the global pandemic was a huge demand on PPE as a whole, so personal protective equipment, around the globe. And it put huge strain on global supplies. And in the UK, I think for several months, there was a lot of fear that doctors working on the front line would be left with improper equipment and not being protected as much as we should provide them with, and that we were doing them a disservice. And of course, for doctors on the front line, they're faced with ever increasing patient numbers, and the threat of infection that goes with that, and also just the pressure of being in that situation. I think at that time of the pandemic as well, we had a rather poor understanding of how quickly this would move, what the associated threats were, just how big was this whole problem going to become. So the strain and pressure on people working in hospitals or care homes must have been enormous at that point. And that really spurred our research to shift from what we'd been doing in the past on CPAP masks into actual protective masks. So the CPAP mask would be somebody who suffers from sleep apnea. They wear that at night, and it's constantly supplying air, oxygen to that person as they sleep. Whilst these kind of masks, this is a protective thing. So this is trying to keep bad things on the outside and not allowing them to come in as you breathe. So you're trying to filter all of that virus that might be in the air, trying to filter that out and allow the people to work safely within these areas being deployed on high risk wards within hospitals. So I think what I want to do now is just kind of define what we mean by a face mask, and the kind of terminology that we're going to use through the rest of the presentation, because I think a face mask is very generic, and we've all probably seen all different types of face masks as well. And this is sort of, I think when you talk to people in different areas, different industries, whether or not it's construction or within healthcare, within hospitals, there's varying definitions on different types. So I think this is sort of my best effort at trying to come up with a kind of categorizing the different types of masks. So over on the left is, I think, the type of mask that we're all very familiar with, consumer fabric mask, very loose fitting, and it provides a certain level of filtration as we breathe in and breathe out to try and capture the virus onto the mask. The sort of other half of this is what we would term a respirator, and that's really what we mean by protective equipment when we get to a respirator. So in here we have two different types again, unpowered and powered, and in the unpowered we have the disposable mask, and this is ones that you would have seen a lot. Many of us would have worn them during the pandemic, but we would have seen many images of these types of masks on the news. This is the sort of FFP3, FFP2, or N95, K95, the typical sort of product names associated with them. And the name of the mask tells us the sort of level of filtration that the mask offers as well. And these are the sort of masks that healthcare personnel were being asked to wear on a daily basis. So they're typically one use, and then you dispose of them. The other side of that category is the reusable masks, and you have a half mask or a full mask that just describes whether or not it's finishing below the eyes or above the eyes. And for these, they're elastomeric silicone sort of based product. It can form to the face a bit better, and you have filters that you attach to the mask. These filters might last maybe a week, maybe a month, depending on the amount of usage, and then you dispose of the filter and place another one on. And the mask is becoming bigger, heavier, more cumbersome as we kind of go right across the screen. And then finally you move into the sort of powered respirator, and this is really where you have a full hood over your head, face, or even you might be wearing an entire suit, a hazmat suit, and then you have a power driven pump that is pumping a constant supply of air through, that's passing through a filter as it's supplied in under the hood as well. And what you find sort of moving left to right across this is that left to right, you're going up in protection, you're going up in cost, up in weight, general kind of, I think discomfort might be a little bit nuanced, but the ability to, say, communicate and talk with patients or with your colleagues is becoming harder as you move across to the right as well. So you have to kind of try to consider all these things. And the group of masks that we're concerned with, or our research was concerned with, and what we wanted to help develop was this unpowered respirator category. So this group here, they rely on sort of three basic sort of tenets to be effective. And the first one is compliance. They rely heavily on you wearing them appropriately and keeping them on, and that really is the most important thing. And I think we've probably all experienced walking around in the supermarket or on public transport, or just walking down the street. We've all seen people not wearing their face mask correctly, and even within locations where you're at high risk, such as a hospital or other sites, compliance is still a problem. It's still one of the biggest factors in health and safety is ensuring you have good compliance amongst your staff. The second factor is comfort, and discomfort is the most cited factor for non-compliance. So anybody has to wear one of these respirators for a prolonged period of time, it can lead to skin trauma, and this can be anything from a rash, pressure damage, bruising, blistering, and of course any of these, once you have any of these complications, any of this skin trauma, it leads to other complications. It can be an infection site, which of course in a hospital is something you definitely don't want to occur as well. And we looked at numerous reports on this, and there's been quite a few audit statistics surveys on this, and up to about 97% of users reported some level of skin damage after wearing respirators for prolonged periods. So it's a significant problem, and you can imagine then the issue of compliance that goes after it. The third factor, and possibly the most important to sort of fundamental effectiveness of the filtration component, the filtration function of the mask, is the goodness of fit. So this is how well the respirator creates a seal between the interface of the mask and the wearer's face. And if you don't have an effective seal, the ability of the mask to prevent the ingress of the virus or other particulate from going inside the mask and ultimately inside you, into your lungs, significantly drops off. So due to that, any user that has to wear a respirator in a location where they are at risk, where it's been deemed necessary for you to wear this type of protection, you have to undergo a fit test. There's a number of different types of fit tests, but the most common is this type of fit test. So it's most common in hospitals, and this is just a sort of a qualitative fit test. So what's happening here is the user, the healthcare personnel, has their respirator on, in this case a disposable respirator, and then there's a hood is placed over the top, and they spray in a bitter or sweet tasting aerosol and just ask the user whether or not they can smell or taste the aerosol. And it's as simple as, if you can taste or smell the aerosol, then the mask is not fitting you correctly, and you do not pass the fit test. So there's obviously a number of different sizes of masks that the user can try, and they can try applying a greater amount of strap pressure as well, to try and force an effective seal between the user and the mask. And of course, with the increase in amount of strap pressure, the increased likelihood of skin trauma occurring as well. So if we've seen 97% of users reporting a high level of skin trauma, or some level of skin trauma, it suggests that most people are having to apply an excessive amount of strap pressure to achieve an effective seal and to pass one of these fit tests. And to give you a kind of a few statistics on failure rates of these fit tests, studies have shown that within healthcare organisations, we've seen failure rates amongst staff up to 90% in some cases. So only 10% of that workforce is passing the fit test, which means only 10% of that workforce can be deployed on the wards in the locations where it's been deemed necessary to have that protective equipment. These sort of failure rates are largely attributed to variance in facial characteristics, so arising from different demographic differences. So this can be anything from age, gender, or ethnicity, amongst others as well. BMI can play a role as well. In the UK, we found that female healthcare personnel are twice as likely to fail a fit test compared to their male colleagues. And some other studies have shown that there's strong association between race, resulting in significant failure rates for non-white demographic groups. So we found groups as high as 25% failure rates compared to white being around about 16% failure rate. If we just take the NHS as a isolated case, as a case study, the NHS has a workforce of around 77% female and 22% non-white. Now, of course, that is going to vary as well between different roles. Sadly, it's not an even spread across all roles within the NHS. But what this does suggest is that this presents a significant risk of a critical reduction in deployable workforce during a pandemic crisis. So if suddenly more wards in your hospital require the use of protective equipment, require people to wear respirators for prolonged periods, more people will need to undergo a fit test. And if they don't pass the fit test, they can't be deployed in those locations. And this obviously has a major impact on morale. Staff want to work, they want to be where they're needed. They don't want their colleagues to have to take that burden. But that's the reality. And that's something that we saw in our research, and we wanted to see if there was a way to rebalance that, to address this inequality in the failure rates. So this was a quote from one clinician in our discussions during our research, where they said to us, "We've been wearing FFP3 masks for months." So this was in the late summer, just as the first wave of the pandemic was starting to level out. Whilst about half of us passed the fit test on commercial disposable masks, many of the female staff do not fit them, and they have to wear positive pressure full head hoods instead. So this is the powered hoods. These are noisy, uncomfortable, and lead to low morale. They also have the risk of contamination, as they're difficult to clean. So not only is it, I guess I probably misled a little bit in saying if you pass the fit test you can't be deployed. There are other options. You can go to this full hood, or powered hood protective equipment. But that comes with these additional complications. Not only, of course, are they more expensive and there's probably less available, there's more maintenance involved. There's a higher risk of contamination because they're more difficult to clean. And there's also the added complication that patients, when presented with staff approaching them with this kind of equipment on, it's not a nice environment for them to be in as well. So they have to deal with that added complication. Something else we found in our research was this isn't a new problem. This problem of bias, of the skewed results in the failure rates, in that they are skewed towards female and non-white personnel. This has actually been known for a while. It's just that the COVID pandemic has put a light on it. And I've just taken a couple of quotes here from a report by the TUC in 2017 that highlighted these issues back then. So that the use of standard US male face shape in the manufacture of respiratory protective equipment means that it does not fit most women, as well as a lot of men from Black and minority ethnic groups. So what they're alluding to here is that the design of the masks that are available at the moment, their shape, their dimensions, their sizes are based on male faces that might not be, let's say, the average male face or the average face in another country. And then there was another fantastic quote from this report that said, "We don't need to be bumpified. Just have the same gear as the men, but with an adjustment to allow a proper fit." So this was taken from interviews with female union members that complained that most of the protective equipment or the equipment they were provided with was not designed with women in mind. So this is a historic issue that has actually been around for a long time now, and it was something that we wanted. It was one of our main aims to address this issue, or find approaches that can address this issue. So where is this issue coming from? What's causing more higher failure rates within women and non-white personnel? And we think that this is linked to kind of historic shortcomings in the design methodologies that are used to design these kind of products. So it's not just face masks, it's not just respirators, but it's the clothes that we wear. It could be anything like joint implants, other wearable tech, anything where there is a sizing process involved. And the way we do this sizing, this is coming under this idea of modularization, where we're going to limit the amount of options or variation within our products. And we limit it so that we make manufacturing easier, so that we can apply a mass production model to our mass production business model. And we do this by something called anthropometric sizing. So this is classifying anthropometric characteristics of a population into a few represented groups, and the represented groups being the sizes. And anthropometric is just means dimensions taken from the human body. So what we're finding, what this creates is modularization creates only a small amount of product variation. And in fact, what your aim is when you apply modularization is you are trying to do the least number of products available to you while serving the largest number of people possible. So if you can get away with one size or one size fits all, that's what you would do, because it's less changes to your manufacturing setup, it's less changes to your production line, and it means that you can produce things faster, certifying them easier, quality control is easier. So the whole approach from a business side, from a kind of lean engineering side, has been this sort of race to the fewest products, product variation possible. So this is just a further sort of indication of what we mean by anthropometric sizing. And essentially what you're trying to do is take a set of standard dimensions. So be it the distance between my eyes, the length of the nose, the width of my mouth, the overall length and width, depth of my head. And then you want to take these on as many people on a population size so that it becomes statistically relevant. And that might vary between different uses or reasons that you're doing, but it might be 1,000 or several thousand people that you are collecting that data from. Once you collect that data, you apply a kind of statistical methods to simplify all of these dimensions down until you've got kind of like two principal components. So you try to relate, you try to relate all these dimensions together such that you can graph all of those dimensions onto a single graph like this. And then what you're doing is just essentially applying a clustering grouping to that to determine your sizes. So this is a very simplified example of that, but essentially this is the approach. This is what we would do when we design a wearable for mass production. And immediately what we can see is there is some proportion here that is outside of our clustering archetypes. So there are going to be some people within that population, that sample population, that none of our sizes actually fit. And then there are going to be people that sit just on the border between two sizes as well. So they're kind of not quite catered for as well. You know, they're not quite a small, they're not quite a medium, and nothing quite works right for them. So in order to create enough product variants, or to find that perfect model that's going to cater for everyone, you would need a sample population that's large enough and varied enough to account for all of the kind of multivariant shapes and anthropometric distributions on all of our faces. And to date, there hasn't really been a product or a study that's been able to achieve that. And the reason being that the numbers required, the population size required to do that would be vast, would be a massive number. And it's just too time consuming, too labor intensive, and it's economically prohibitive as well. So this is why we have this inherent issue in any product where we offer a limited variation in sizing. There will always be people that it doesn't fit. So the way around that is to customize such that everybody has a one-off product. Everything is tailor-made and is completely bespoke and personalized, customized to you. And during the pandemic, there were a lot of projects, products out there that offered this service or showed people how to achieve this service for their respirators. Most of them focused on 3D printing to enable this, and they either via journal publications or internet, they showed you how to do this. They provided you with tutorials to do this as well. And the problem with that is that it relies heavily on the user having a good understanding, or an expert understanding of the design process, access to the software to change the design, access to the equipment to manufacture the mask afterwards. And for us, most significantly, the problem here was that the production time, the time taken to get the user information, which in this case was a 3D scan of somebody's face, process that through a design or CAD package, and then manufacture the part. This took too long and was too reliant on manual labor for it to have any kind of meaningful impact during a pandemic crisis like the one we've just experienced. And the reason is inherent again in the design process. So the way they're reliant on taking a face scan. There's lots of ways that you can get that, and I'll touch on the different devices that you can use. But then you enter into this manual, skills-driven methodology where you have to do post-processing to the scan. You'll need to clean it up. Typically, these scans come with some errors, noise, defects in the scan which need to be checked, looked over and removed. And then you are reverse engineering, so you're rebuilding the generic or the master design of the mask such that it fits your face. And then finally you can output that and send that out to manufacture. So it was about, I think about a month, 2 months into the first lockdown, we'd sort of completed this first bit of research, just trying to survey the landscape, see what the problems were, see where we might be able to make a difference. And whilst there was a lot of great work going on to address the global demand in PPE by augmenting supply lines, searching for new supply lines, we really wanted to focus on the design of these and try to find a kind of approach that would create a legacy that would hopefully remove these problems from any future pandemic or any future crises where we have a sudden global demand in this type of equipment. So we began this project, which we called the Mensura Mask Project. The aims was to create a single platform that was capable of creating customized face masks, respirators from 3D facial scans. We wanted it to have no requirement from the user to do any manual handling of the face scan. So anything about reorientating that scan, rescaling it, repairing it, checking for errors, anything like that. We wanted our process to be able to handle all of that automatically. There'd be no requirement for the user to have any prior knowledge or competency in CAD or design packages, or to carry out any manual manipulation of the CAD model themselves. And then the output from this process would be a part file that could be sent immediately out for manufacture. We received an amazing response from this project, and it was picked up by CNN and the BBC, amongst a few other international news agencies as well. And because of that, we were able to get a kind of participant response or volunteers that we needed to run our research project. And that involved people taking a scan of their face using a mobile phone, and then submitting that scan via our website. And then we would send back to that participant the part files of their mask and instructions on how they can manufacture. So it was a little bit reliant at that stage that the participants in the research project would have access to their own 3D printer or somebody else's 3D printer, and they could print their mask. And I've got here a couple of tweets from people that managed to do that, and thankfully gave us reasonably positive feedback on the whole process. And actually this running this project during lockdown, during this pandemic, created a whole new set of challenges as well, because typically if we needed to get as many volunteers into a project as possible for something like this, which was just 3D scanning your face, we would set ourselves up somewhere on the university campus and offer to buy students their coffee, their lunch, or a voucher for the student union bar, and we would have no problem having the sort of number of volunteers that are required to make something like this statistically relevant. So if it wasn't for if it wasn't for the BBC, really, we would have really struggled to get the kind of volunteer response that we needed. But it really did challenge us to think new ways to run these types of research projects and how we could do them online, which was quite a new challenge and process for the university to go through. So I touched on this sort of manual customization approach, and ultimately what we're trying to do is turn this customization approach into a mass customization approach, one that is scalable and applicable to be delivered to the masses. And essentially what we're doing is we're taking this manual section of the process and replacing it with an automated, fully automated pipeline. So the first step is getting a raw facial scan, a 3D scan of your face, and something like this. And to do that, we looked at various different methods, devices to get these scans. We wanted to check different modalities, different environments, different lights, to sort of check on accessibility and viability within a healthcare setting, or within is this viable to the public? Is this viable to only hospitals, or can we roll this out to construction sites and so forth? So we were looking at a number of different metrics, as in cost and accuracy and viability. And we had 4 different processes we looked at. So the first one is this pulsed blue light handheld scanner, and this is a very high resolution, highly accurate process of scanning a 3D object. But this equipment costs around about £20,000. It takes quite a while to scan an object, even just a relatively small object like your face. And actually there's a lot of post-processing time afterwards. The next method we used is a photometric process. This has a number of cameras placed in known locations that are spaced, the angle between each camera and the location of each camera relative to each other is known. And then where you are relative to the cameras is known as well. And then they take a series of high resolution 2D images. And then from that, you can stitch them all together to create a 3D model. But these processes, they vary in cost and in size, but they can be up around the 50 to 100K mark. And they produce incredible color, texture, resolution. But the cost and mobility of this process is very prohibitive. And then the next 2 processes we tried was this. The 3D scanners are available on some mobile phones. And we also use this 2D image process where we predict a 3D face from the 2D image. And what we found as we kind of go left to right through these is that left to right, we're kind of going down in accuracy, down in resolution, but we're going up in scalability, up in viability, up in deployability. So you had to find a kind of happy position somewhere in here. And what we feel our results have shown us is that the 3D scanning technology available on a mobile phone is more than adequate for this type of application, and I think most applications within the medical realm as well. At the moment, this technology is available on iPhone 10 and newer, and it's the Face ID technology that's available to unlock your phone. So we tap into that equipment and build a 3D scan of your face from there. Okay, so next, once we have that 3D scan, we need to undergo what we call sort of a digital face fitting. So this is we use a number of different processes, a number of different sort of smart algorithms to take an average face and morph that to your face. And by doing that, what that allows us to do is it allows us to create a model that's exactly your face, but where we know where every point on that face is. So the point on the end of the nose in that scan, in that mesh, that has that data point in my list of data is always in the same location in that list. It always has the same index number. So if I'm telling a computer what data point is the end of the nose, it's always that same position in the list. It's always got the same index. But what's changed is its spatial position. So that point on the end of my nose is going to have a different spatial number to the end of the point on the end of your nose, probably. Mine's probably going to be a bit further out. And then from there, we can select a region of interest. So then we can extract that topological data, the contours of your face that we need to build the customized mask, the custom CAD model, or any facial wearable or any other wearable that we want through this process. So because we've gone through that face fitting, now we can always, with high confidence, know exactly where our region of interest is and then extract that data. Once we have that data, we can import that into a CAD environment, and from that we can automatically build up the CAD model, the design model of that product. So this video is just sort of showing an example of that process. This is quite an early iteration of our design and our codes. So this is actually run in something called Fusion 360, which is a CAD package by Autodesk, and we use something called an API. So what these allow you to do, and they're available in a lot of different CAD packages now, but essentially rather than manually clicking on different functions, places in my CAD package, which I would typically do to draw out sketches and extrude parts to build up my 3D model, instead I'm coding it. I'm writing out a list of instructions that that CAD package is then going to follow through every time. So once I have that region of interest, it's just following a set of instructions after that, parametric rules, to build up this 3D model. And sort of since then, what we've been able to do is implement this whole process in one environment. So it's going from taking the raw scan all the way through to outputting the part file required for manufacture, all in a single seamless process. So there's no manual clicking that you see in the video. Okay, so once you have passed through the design pipeline, you've got your CAD model ready for manufacture, and the way we do it, and really the only manufacturing process that will enable this type of approach to these products is 3D printing. And the reason for that is that 3D printing gives us an opportunity to change the design of the product every time without any cost penalties. So typically a face mask will be done using a kind of a hot pressing process for this, or the stiff fabric based ones, or a kind of injection molding or casting process for the polymer elastomeric masks. Those molds that are needed in either of those processes, those molds are very, very expensive and very hard to manufacture in the first instance. So you don't want to change the design of your product, because you're going to have to pay for that cost again. And that again is the whole thing in a nutshell of modularization. You are trying to limit your outlay costs for how many molds you need to buy by reducing the product variation that you offer. Whereas what's happening here is every product is different. Every product has changed design. Everybody has a slightly different, slightly unique facial shape. And therefore you need a manufacturing process that allows you to do that without having to pay significant costs each time. And 3D printing, because there isn't that tool involved, the 3D printer is the tool, and it can print anything that you want within reason. So the design can change each time. Okay, and here are some of our results, some of the early masks that we made, and some of the team members just demonstrating the difference in facial characteristics and the kind of the goodness of fit that we were able to achieve through this process. From our website and from the kind of response that we received from the BBC coverage and other coverage, we managed to very quickly get to 299 web submissions. Of these, 205 were usable. Up on the website, there are instructions on how to take the face scan and some of the requirements. So, for instance, one requirement for the product is that you don't have a beard. If you have a beard, it's obviously creates a porous layer between the respirator and your skin, and it cannot achieve a good seal. So anybody with a beard would not be deployed into these sorts of locations where it's required, or they would have to wear a full face hood. And I think we had quite a few scans with people with beards on. Glasses is a problem with the process at this stage, so we requested people to glasses. So there's a few things like this where we had to whittle them down, but essentially we had 205 usable scans that we could pass through the process to check how well it is performing. And of that 205, we had a 96% success rate. And what we think that means is that we would have 96% pass rate. So 96 people will have, or 96% of that 205 will have a completely bespoke mask, completely tailor-fitted to them. And what we're able to do, and why I feel we're able to make that statement, is that we can analyze the digital fit of the mask to the individual. So using the CAD model that we created, using the 3D scan that was submitted, we can place the mask where it should be worn and look at the distance between all the points on that surface of the mask that makes contact with the skin. and see what those distances are. And effectively, what we found is that you're always going to have a few points that might be slightly higher or slightly lower, and there's there's going to be like a threshold distance where the natural compliance of your skin, of your soft tissue, means that the mask doesn't work. So as long as we were in a kind of 1 to 2 millimeter range, we felt that was a very good fit. And analysing the kind of demographic data that we had with the 205 scans, we're able to start analysing, is this process bias? Do we still have that same inequality that we're currently seeing in with the current commercial models? And what we're, I don't want to kind of pick this table apart too much, just because it's probably not that interesting or exciting to look at. But essentially, what we've been able to find is that this initial data, this initial small study, 205 is only a small study, but we found that there is no variation between different demographic groups. So all demographic groups are catered for equally, which was a fantastic finding for us to realise. So where we set out from for this project, we feel that we've achieved all of those initial aims to create a single platform, that there's no requirement on the user or the customer's side of things. So they don't have to have any experience in design or CAD modeling or manufacture, and that the pipeline, the software, the codes that we've developed can handle all of the issues automatically, with an extremely high success rate. So where are we going to go next with this? We are just starting our second round, our second, let's say, digital study, where we're going from around 300 faces to 3,000. And in fact, anybody here, if they want to take part, please do. We're always happy to receive more volunteers, more participants in the study. Just go to the Mensura Mask website, and all the information and instructions there on how to participate and what's required. And of course, if anybody wants to contact me as well, please do about it. So that's currently ongoing, and I think from this larger study we'll have more statistical relevance to be able to make these statements about overcoming bias. And we're also starting our physical testing as well. So far this fitting data is digital simulation, and what we will be doing now is taking a sample population, most likely students on the campus now that they are hopefully returning over the summer, and we'll target demographic groups that are higher risk of failing current fit test. So we'll compare a commercial respirator mask, something like an FFP3 mask, and we will ask each individual to try a fit test. Hopefully some will fail, and we'll take a 3D scan of each of our volunteers, and then we will 3D print their subsequent customized, tailored mask and ask them to come back and undergo a fit test again. And hopefully what we'll see is those that previously failed with the FFP3 mask will now pass. And we have very high confidence that that will be the outcome of it. The other challenge that's come out from this, for making this kind of a process, this kind of approach to the design and manufacture of wearables, is certification, and that's a very big issue for medical devices or personal protective equipment like these are, is ensuring that they meet standards and they've been certified as safe. Those certification processes are set up for mass-produced products. They're not set up for products that are one-off, that change every time. So we will need to be in consultation and look at, develop with this industry, with this market area, with these certification bodies, new forms of certification that can adapt to this type of product offering. What did we learn from this process? The current methodologies suffer from inherent biases, and that was the biggest finding that we had, looking at the different audits and survey statistics that are out there, and that female and BAME users are poorly catered for compared to white males, and that a new design methodology is required to overcome issues that are inherent in this modularization approach, and that customization offers a solution, but it is reliant on a manual, skills-driven design process. And in order to get to a mass customization process where you can offer that tailor-fitted thing to every individual, it's got to be automated, so that it can be viable in terms of speed, scale, and cost to things like the healthcare services. And that apologise for the lights in my office, they keep flicking on and off. They're automatic, I can't do anything about them. The other nice finding that we had was that you need to gather that user data to make these kind of products, and in this case that's a 3D scan of the face. The ability to do that is essentially at your fingertips. It's in your mobile phone. So harnessing that technology is absolutely key to this kind of product offering, but it's there, and we just need to take advantage of it. And what does the future hold for all of this? Well, we've seen a lot of development over the past decade in this area, and I think with COVID-19, that's really created the media attention that this area is needed as well, to kind of really accelerate this process. And I think that mass customization in the wearable industry as a whole, so not just respirators, but I think in the entire wearable industry, that will become commercially available in the next 5 years or so. So whilst I've concentrated on faces in this presentation, the process that we've developed can be applied to really any body part. So it could be other therapeutic or protective wearables on other parts of the body. It could be the footwear, your shoes, your trainers that you wear, taking a scan of your foot and mass customizing all these things. And we are in the process of commercializing this project with the support of Imperial College into a company called Polymetrics, which hopefully you'll all hear lots more about in the years to come. Which leaves me on my final slide just to say thank you all for coming and listening to me for the last, I think, 45 minutes. And also just to say big thank you to all of my students, research assistants that are involved in this project one way or another over the last 12 months, and made all of this possible. And one more final plug for our Mensura Mask project. Please do visit the website. Please do participate in the study. The more people that participate, the closer we'll get to eliminating bias design bias in these types of products, and coming up with a method that can be scaled out across all these types of protective equipment and medical devices. And I'm happy to take any questions there may be. Right.
So we've got quite a few questions.
Excellent.
A lot of them, a decent number of them relate to the idea of sample size. So if we're talking about the population that you're talking about, what is the sample size? You said it's vast. We're talking millions of data points, billions?
Yeah, okay. So yeah, that's a really good question. I think if we're talking about the design of a mask, effectively what we're saying is that the larger your population size, the greater the probability is that you are capturing all of the variance in the anthropometric data. And your design is only ever going to be as good as your population size if you apply that design method, the methodology of modularization through anthropometric sizing. So I'm not a statistician, so I don't want to, and I think it'd be appropriate to just say it's 100 or 1,000 or something like that. It's dependent on what the outcome is that you're looking for, and the amount of variance that you find through that population. But the point that I was trying to make or allude to is that the variation in facial characteristics across the globe is so large that you just wouldn't be able to run a study large enough to gather as much anthropometric data as you would need to account for all of that variance, and then cluster that well enough to be able to say, oh yeah, these are the 4 sizes that we will offer, or 10 or 20 sizes, and say this will cater for everybody around the world. I would challenge a company or a research team to demonstrate that. I think that the problem, the population is just too large.
Okay, no, thanks very much. And if we're talking about producing masks, how do you scale up the individual CAD models based on photos to thousands of user requests? How do you scale up this programming on a large scale?
Yeah, so the right now, I think we've managed to get the processing time per person down to a minute or 2. It's in the minutes, less than 10, right, from them submitting to a response. And it doesn't require a lot of computational power. So a service like virtual machine service would be able to handle a lot of traffic quite easily, and that's how you would scale up. You would be looking at this is a completely automated process. There is no human interaction. So from submitting the file, that is flowing through our pipeline and straight out to manufacture. There's no bottleneck there that's reliant on a human interaction, and the scaling up process is just that it's completely automated. So we just need larger computing capability, and all that technology is there and available to us to outlay this type of offering. And one of the things that I didn't touch on here is, one of the things that we can do with this type of coded design and what 3D printing enables is that all of the user information, let's say a physical barcode, can be embedded on the mask as well. So we can streamline all of that process. All the information that's required can go straight to the manufacturer, to the 3D printer, and then once that part is taken off, it has a unique barcode symbol on there that then tells us exactly who that's for and where it's got to be sent. So all of these things can be streamlined and implemented into the process.
Okay, no, that's really interesting. In terms of standardization of this sort of process, have you engaged with any bodies such as NIST on this?
Sorry, in terms of the standardization?
Yeah, so the process standardization and the
No.
idea of having a few sort of basic mass concepts that then are customized.
Yeah, no, I haven't. We haven't done anything with MIST or NIST. Sorry, I misheard you.
NIST.
So
yeah.
the design of the mask is our own, and that's, again, it's publicly available. The generic design just via the Mensura website. If you had another application, so it wasn't protective equipment, it wasn't a respirator for protective equipment, but maybe it's a respirator for another type of medical application, you might have a slightly different design spec that you need, and that's fine. So you only need to design that once, because you're designing it parametrically. You're writing into your code the set of instructions to rebuild that every time, and how that is related to the user data, the region of interest that you're taking from the 3D scan. So yeah, you only need to do that once, and then the rest of the pipeline is the same. And it's always customizing that particular product. I hope that answers the question.
I think it does, or at least I hope it does to the student's satisfaction. There's more of a comment here, but I'll phrase it as a question. Do you think that part of the issue with mask fit in the past has been because of a bias in biometrics, where there's been sort of a standard face, and it's been assumed to be sort of a white male doctor in the US?
Yeah, I do. I think that's exactly the issue. As a white male, I think that too much has been done by white males with only white males in mind, and I think the failure rates in just taking this one product in isolation, the results, the statistics speak for themselves. It's very clear skew in failure rates, that women fail far more often than men, and non-white men are more likely to fail than white men. That cannot be argued with, and it does then make us question why is that? As designers, what's happened there to mean that it's only working for this one demographic group? And it's because however many decades ago, when that design was developed, the population that it was based on was predominantly white men, and therefore the product predominantly caters for white men. And we can try and do, as I say, we can try and do larger population sizes, but I think that there will always be some level of groups that are not catered for. So if you can get a bigger population, more variants, within that population, you've got an equal spread of male, female, different ethnicity, different demographics. You will have a better product offering across that set. But there will always be people that fall outside of your sizes. And I think that's the only way around that, is to move to a customized approach.
Okay. No, that yeah, definitely makes sense. And thank you for that. Sort of on another bit of a sideline. So you've talked about fit and comfort helping compliance in mask wearing, but do you think that there are any other measures that could be implemented to ensure compliance?
Yeah, definitely. There is, yeah, do we want to go down those routes? I mean, we're talking about monitoring user behavior, and enforcing compliance. And I think in many locations that's probably not practical or not ethical. So yes, there are other options, but I think that they're not the best options.
Yeah. And if we look at feeding into the Mensura mask project, so is there a cost to the user? What would be the turnaround time from scan to delivery? And then related to that, somebody's asked, Scandi Pro and Bellis 3D have an in-app purchase. Which purchase is needed for the scan to be done and submitted to you?
That is a great question, and one that I should know off the top of my head. I'm hoping that one of my students is going to message me quickly so I don't make a complete fool of myself here. I believe that the information is up there. If not, that individual, please email me and I will respond to you. Scandi is free. Here we go. I'm getting fired. Scandi is free once a week. So if they only do one scan per week, you can use Scandi. So yeah, Bellis, you need 99p per scan.
Okay. And in terms of cost to the user to get one of these masks, or to the purchasing officer, say, what are we talking about here?
Yeah, that's going to vary, and it's sort of difficult for us to put a number on. If you have your own 3D printer at home, and actually that's not as crazy as it sounds anymore. If you have a material extrusion printer, so an FDM or FFF printer, one of these like Ultimakers, MakerBots, this kind of a printer, the actual cost of the material is very low. We're talking less than £1 worth of material. The other alternative, which we think is better in terms of the surface finish and the quality of the build, is to use a vat polymerization approach. So this is like a Formlab type printer. The material then is a bit more expensive. We're talking maybe some £5, £10, £15 worth of material. If you outsource to a 3D printing provider, it's going to be more, I'm afraid. So we would love to offer that service. We just can't. We can't do it at scale and deliver the kind of outlay, delivery, postage, and so forth for it. Also, we fall into a grey area of now we're providing a product and who's liable. So if you want to be a participant, if you want to, we would love to have the 3D scan and it can just end there for you. If you want to make the mask, but please do read the terms and conditions. Be aware of, these masks are not certified as yet, so we cannot guarantee that level of, the level of protection. But I would say they are, they're the same as a a fabric mask that you're buying in your local corner shop. It's no difference there, basically. Yeah.
In terms of materials, actually, because this is something where I have had a bit of exposure to it, there's a significant variability in the flexibility of polymers that come from different 3D printing processes, and levels of shore hardness, that sort of aspect. It's been difficult finding low shore number elastomers for this sort of thing.
Yeah,
How did you manage to identify this?
Yeah, okay, so what we focused on was actually what's skin safe, and that's the key factor, and it's skin safe for prolonged periods, because of course you're going to be hopefully wearing this kind of product for a while, minutes or hours. So that's the most important factor to us, and there's a list of materials on the website that's suitable, and thankfully for the FDM, these are commonly available and not expensive. For that polymerization, because we're talking about photo resins, it's a little bit harder to come by, and they're a little bit more expensive. Materials is one of the challenges to outlaying this kind of a system. But what I would say is that the additive manufacturing industry, the companies that produce the machines that develop and supply the materials, it's such a rapid industry at the moment. There is constantly new materials becoming available, new materials being developed, new technologies being developed and becoming available. So right now there are skin safe materials available to do this. There will be many more, and I know of more that are coming out, even in just the next 6 months, a year. And I think as well as, this is these sort of push-pull situations that you have with new technology. The more that customers demand this, the more industry will develop and meet that demand. So while we are developing and dealing with the design processes required to scale up this kind of customization process, there are multiple 3D printing material developers dealing with the other side, that is making printers that are fast enough, that have the accuracy, repeatability, and can do it from the materials that are required. So, I've touched on skin safe, and you mentioned about flexible materials, finding that right in there, and that's something we've kind of focused on rigid materials, and we found them to work really well. We would love to start trying flexible materials as well, to get that extra layer of compliance and comfort in there. But what I would say is that with the elastomeric, the reusable respirators, so these are the half masks and the full face masks, and these typically come with a very large silicone or elastomeric seal. That's on there to account for the large variation in facial types. If you're, so it's on there for that, not for comfort, right? And obviously it helps with the comfort, but it's primarily there to account for the variation in facial shape. And if your mask is already fitted to you, you've already got that perfect snug fit to your face, you don't actually need a large elastomeric cushion there. It actually creates a very comfortable snug fit, and you don't need much strap pressure because it's essentially fitted on. You're getting a nice equal pressure all the way around. So even then the strap pressure is greatly reduced. So even with the rigid materials, we found, anecdotally, we have found that comfort is greatly increased.
Okay, no, that's great to hear. There's lots of questions, and I'm sorry that I'm not going to get through them all. We've got time for one more. And in order to keep this sort of a bit more general, I'm unfortunately having to avoid some of the higher rated questions, but the one that seems of wider general interest would be if this process can be applied to other wearable devices as well, or if you've thought of this process for other devices that you've been developing within your research group.
Yeah, that's exactly what we're doing, and what we want to do with it is just see how many different products are available on this. We have research projects going in articular joint implants, so this is hip and knee replacements, and we apply the same thinking process, slightly different approaches, slightly different data acquisition methods, different methods to get into that 3D model step, but it's still the same kind of automated customization approach. And another area that we're building in footwear, you could imagine the high street, your high street experience changing dramatically in the decades to come, in that you don't go to the shoe shop anymore and look at the wall of shoes and ask if they have in your exact size, or realize that Nike don't quite make the right, they're a little too thin for your shoe or something like this. Now you're going to go down, you're going to get your foot scanned, we're going to take some other data as well, maybe we'll get a pressure map, see how you stand, and then how you walk. We gather as much information as we can, and then we build all of that into a parametric model of that shoe for you. So then you come back, the next day or a week later, or we post it to you, and you've collected that shoe that is now completely bespoke and fitted just for you, and not just the shape, but how you use it as well. I do think that is the future of all of these consumable products.
Thank you very much. No, that's great to hear, and it's something that I think we've sort of seen the start of for some shoe manufacturers, but it'll be interesting to see how the area develops even further.
Yeah, exactly. All the big players now are doing some kind of 3D printing product or sole or insole or something like this, but I think taking full advantage of that is going to a customization approach.
Cool, thank you. At this point I hand off to Rimesh.
Yep, thank you so much, Matt. Okay, so as we look to close our Q&A, a big thank you to Dr. Myant for explaining the innovations required for this brand new industry, and thank you to Matt for co-hosting. The doctor's details are within the chat, so if you've got any more questions or you need to reach out to him, please do make contact.
Please do, yeah.
Yeah, right. Okay, so now for our closing slides. We hold monthly evening lectures and some daytime lectures, so please go to the IET Central London network events booking system, where you can view any more events that you're interested in. And don't forget, you can also collect CPD certificate for attending the sessions. We've also put a diversity survey into the link, so into the chat box, so please use that link. It'll take you a couple of minutes and it will help the IET gather the data. And if you want to continue this conversation online, please do tweet or Facebook about this event. But that's it for today, so thank you for attending and have a good evening. Thank you.